Good morning, everyone, and welcome to the Friday Informatics Power Talk series. I'm very happy to introduce today's speaker. Dr. Ryan Godwin is a data scientist in the departments of anesthesiology and radiology. He's also a faculty member, and he teaches courses such as the applications of artificial intelligence in medicine course for the Martin F. Heersing Institute for Biomedical Innovation. He completed his bachelor's in astronomy and physics and also a master's in applied physics at Northern Arizona University and a Ph.D. in physics at Wake Forest University. I know he's going to introduce himself too, don't want to steal his thunder. So without further ado, Dr. Ryan Godwin, Informatics meets MLOps, building and scaling AI ML models effectively.
Great. Thank you for the kind introduction, Amy. I appreciate it. Yeah, like Amy said, I am a physicist by training, and have a very diverse background in terms of what I have done. I got an undergrad degree in astronomy and physics, and then had this realization that no matter how good of a astronomer you were, you might get rained out and you just were at the whim of the weather. And I didn't like that idea in terms of performing science. So I leveraged a master's degree to sort of transition into the biological fields. Oddly enough, after I got my master's degree, I went and worked on the telescope. It was called the Discovery Channel Telescope at the time. Now it's the Lowell Discovery Telescope, but it was largely funded by the Discovery Channel founder. And it was a really awesome project. And that's where I learned a lot of the practical concepts that I'm going to sort of describe today. And as I pursued sort of computer-related research, a lot of those engineering principles came in very handy, as you'll see, hopefully, throughout my talk today. I also dabble in entrepreneurship. I've got a control system company that with collaborators from the telescope, and we have biomechanical installations, software running biomechanical installations down in Arizona, and a variety of other projects that we've done. But it's amazing how telescope software was readily repurposed to biomechanics software using some of these ideas that I'll talk about today. And I've also got a data science consulting company called Blaze Pascal. Done a lot of different research from proteins and DNA, molecular dynamic simulations to radiology AI type work as well. I have a primary appointment in anesthesiology with a secondary appointment in radiology. So what I'm going to talk about today is this idea of MLOps and how we can use it to expedite building AI ML models, and not just expedite them, but build them in a way that's robust and that we can review and audit reliably and have lots of confidence and trust in as we push them out. Because at the end of the day, we want to build things that people are going to use. But in the healthcare situation, of course, we have to know that things are working right. We have to vet things very thoroughly before we put them into clinical practice. So hopefully this description of building a bridge will sort of help you piece together why some of this comes in handy. So when I started developing software a long time ago, it was just so easy to start coding. Software engineering is a really unique form of engineering where you can just start your project without having to do any kind of pre-planning. If you're a mechanical engineer or a civil engineer, you're probably looking at drawings and designing and thinking really hard before you ever start building. Software is a little bit different in that we have a tendency to start building straight away and seeing what works as we go. And there's nothing wrong with that, because sometimes when you're building a bridge, you just want to see if you can get to the other side, right? So maybe laying a log down and walking across that is all you need, and that's totally okay. And in those situations, starting coding at the very beginning, proof of concept sort of work, totally makes sense. And it's not necessarily pretty, but you can get to the other side. But much more often, we want to build software or bridges that people will use and trust and find reliable. And so that they come back to time and time again because they didn't sprain their ankle or fall in when they went across the last time. So, and even a bigger goal is to build bridges that are useful for a lot of people for a really long time. And then maybe even if you're lucky, have some sort of aesthetic appeal. So that's my sort of analogy of building bridges is like building software. And as I say this, I also want to preface some of my talk with I'm a preacher's kid, so if I sound a little preachy, I do come by it honestly. So full disclosure there. But why does this matter? This is a really interesting paper. It just came out this week, published in JAMA, about FDA-approved AI applications in healthcare. Software as a medical device is most of these approvals, sometimes called SAMD, and you can see that it's just skyrocketing. So the FDA has a lot of things in place, a lot of expectations of people writing software as medical device code, how they structure it, how they frame it before you can get FDA approval. And you can see that this is just taking off. So we want to build for this idea of translation. We want to build the robust bridges that are going to get people across reliably and that build confidence, build trust, and at the end of the day, help the clinicians provide the optimal care for their patients. So what is MLOps? I found this, I thought it was a pretty interesting take on it. The old way of writing software, you could just think of it as needing to look after the code, because that might break your data. But when you start thinking about ML systems, machine learning systems, really the model, the code, and the data comprise the system. And any one of them can betray you at any time. And so this idea of garbage in, garbage out, that's your data. The idea of model drift or other model collapse issues that you might have downstream once you've deployed could fail, or the infrastructure in between. Maybe there's a big change in packages, or maybe there's a big change in structured data somewhere along the way in your code base. So you have to start thinking about this as a comprehensive system that involves the data, code, and the model. So one of the really important considerations for building reliable ML AI tools that could maybe someday be FDA approved is record keeping. And I love this quote from Maya Angelou: if you don't know where you've come from, you don't know where you're going. And I think that couldn't be more true in the case of AI applications, particularly in healthcare. I thought this was fun. I play with generative AI a lot. And in March 2023, I gave DALL-E 2 at the time this prompt: a human stenographer sitting in front of a typewriter, sitting at a typewriter in a courtroom, recording a robot giving a speech as a DALL-E style painting. And this is over a year and a half, same prompt, DALL-E 2 to DALL-E 3, but just the stark difference in quality. The models have really gotten amazing. And this isn't an LLM or a generative AI talk, but having some record keeping allows me to make this slide, right? Because I remember what I did back in 2023. I kept a record of that. And now I can have that same prompt ready to put in right before this talk. And now you get the DALL-E style melting stuff. And I don't know, it's just really amazing to see how things have improved. And I couldn't do this without keeping track of it. But there's more to that idea, and we'll get back to that in a little bit. But another good machine learning principle is considering the full data lifecycle. In that JAMA paper as well, they talk about this, and it's worth reading that if you have a chance. But there's a life cycle to data, and the NIH has bolstered their guidelines and their expectations for your data management, and having a data management plan you put in for an NIH grant is a really important piece to it now. And having some structure around your data management plan is really important. So you need to think about how you create, store, use your data, share it, archive, and destroy as you go through the data lifecycle process for any project, but especially so in healthcare. And along the lines of recording and documentation, there's a suite of tools that really facilitate this. And I should preface this with the vast majority of what we do is Python. I suspect many of you doing informatics, AI work are also working in Python. That is to say, it's not exclusive to Python, but a lot of what I'll present today is in that context and easy to use if you use Python, and actually readily deployable in the Python sense. And we'll talk about that. But MLflow is a fantastic tool. We think of it as our digital lab notebook. So if you came from a traditional bench lab, you had your scientific lab notebooks, you would write things out. I remember when I started my PhD, I was literally printing out graphs, physically cutting and pasting. I'm dating myself, I know, but into the lab notebook, and I was like, there has to be a better way. This is long before MLflow. Eventually, we had a tool that we use in our lab, but it's important to have digital record keeping, tracking any kinds of runs, so you can track your hyperparameters, track any of your optimization efforts, and then have a record of it that you can go through and see what you did, when you did it, how you did it, what you got, and just access that and have that full record of the experiments as you go. And then there's a number of other tools that we love to use all the time for our machine learning options, or machine learning operations rather. Mintlify is a fantastic tool. There are other tools very much like it out there now, but it's an automated code documentation tool. You can see in this video, just with a couple of clicks, I'm able to take this generate map function and say generate documentation. And within seconds, it's going to read my inputs, read my outputs, and describe what the function does. So it's important to document your code to know what it does without having to read through all the lines. And it really facilitates collaboration because your colleagues can see what your intent was and check your code and make sure it does that. So the overall strategy that we're deploying in machine learning operations is really just to be principled in advance. Think about dependency management. If you've done this enough, you know that package management is a bear, and sometimes can just be a big old thorn in the side of a project. So thinking about dependency management, versioning, not just the software, but the models and the data, because we're thinking about the whole thing as a system now. Having a cohesive code style, directory structure, facilitate collaboration as well. You know where things are going to be, even though it might be a different type of project, you have a structure that guides where things will go. Configuration management, documentation are all really important pieces to this. And so we have these suites of tools. Some I've talked about, some we'll talk about some more in a little bit. But you just want to make it easier to do right than to do wrong. And as you think about building these things out into FDA, hopefully translated software, you really have to think about regulation. This is an excerpt from that JAMA paper that came out this week. And they're talking about they want to see people using MLflow. There's another tool called Deep Eval, which is a large language model evaluation tool. Has a suite of metrics that are built in for evaluating things like hallucinations or summary quality, so on and so forth. But the FDA is looking for these things, and clinicians are too. They want to know how have you validated and vetted and made sure that you did it once and you can do it again and reliably and trustworthy manner. One other piece that's not necessarily part of this template that I'll talk about in a minute, but that we use a lot and I highly recommend for any of you, is checking into the packages before you dig too deep. There's a great tool called snic.io advisor. And this will tell you, it ranks essentially all of the packages you can imagine, as long as it's a pip package or NPM. There's different package management tools that you can select from, but it'll rank it and it'll tell you how popular it is, how maintained it is, what the community is like. This is the score for NumPy, very popular, ubiquitous tool in Python programming. It's a great score of 94 out of 100. But other tools that we have tried in the past, Mr. SQM, not so great. It's a 57 out of 100. And this is just a great tool. It's easy to say, hey, I want to find a Git repository that does this thing that I need. You'll probably find one. But not all things that Google provides in that search are equal. Some are going to be way better than others. So we use this page often. I highly recommend it if it's not on your radar to check it out. It's a great way to just not get yourself losing a half day to some poorly developed code that someone pip packaged up and made available. So I highly recommend that. And then at the end of the day, really, we just want to synchronize our projects and make them look and feel the same. So whatever project we're working on, we have this structure of an operating system wrapped in VS Code wrapped around that, and then we Dockerize all of our stuff so that we're really isolating our package management, our software from everything else, and we just get these nice, consistent packages that are styled the same way, that look the same, they feel the same, and really makes life easy. And you might be sitting there saying, this sounds great and all, but that's a lot to do for every project, and you're absolutely right. Got to iterate quickly, and there's no time to do this every time you're starting a new project. Totally agree. Here's another 1.5 year separated DALL-E prompts about someone trying to juggle a lot of work. It's amazing to me, the quality difference. But how do we do that? A template. Templating is a fantastic tool. The control system software LLC that I am a co-founder of leverages templates in our control system software. I brought that kind of idea into the work that I did for my PhD and now doing here. And we use a tool called Cookie Cutter, which allows you to template out a structure. And we have built a machine learning operations template that includes all of those software packages, MLflow, Mintlify, consistent style guides through Flake and PET8 enforcement tools. It manages your container. It does all of this out of the box for you. So if you're able to snap that QR code, if you're interested in trying this out, we'd love to have people use it and give us feedback. We published this earlier this year as well in Software X. So really, really handy tool. And then as we move forward, everything else that I'll show you today essentially is built on top of this structure. So I'll pause there for a brief second if there's any questions about the MLOps idea before I get into specific use cases and the applications of how we've deployed this tool. All right, well, feel free to ask questions at the end. So one of the projects that we've worked on and recently published a letter on is this idea of estimating vascular stiffness using this idea of pulse wave velocity. So as we age, our vessels don't work as well as they do when we're young, and that stiffening of the vasculature causes problems. It just increases the stress on the vascular walls. We're not able to absorb that energy into an elastic potential energy and then return that into the vascular system as the pressure decreases on a pulse, a beat of the heart. You get this big spike in pressure, and then that's how it distributes through the body. Something called the Windkessel effect is like how the aorta, for example, expands on those big boosts and pressure waves, and then it relaxes. And that's the pulsatile way that we measure our pulse, for example. But as I said, as we age, that doesn't perform as well as it does when we're young. So here's just a couple plots from a famous blood flow book called McDonald's Blood Flow and Arteries. And you can see in the figure on the left, we have large diameter changes over pressure changes from about 75 to 130 for a young person, 26 years old. And then on the right, 77 years old, we see much, much smaller changes in the diameter. And so this idea is what we want to use to try to estimate people's vascular stiffness. So the big goal of this project is to get to a place where we can essentially approximate someone's vascular age. But there's a lot of validation that needs to be put into place before we are able to do that. So we have this set up where we have a high resolution data capture platform called SickBay, and we examined a cohort for this initial project of patients in the cardiovascular operating room, and the consistent hardware sensor suite that the patients we were investigating had are ECG leads. So they had these 5 ECG leads shown in the figure there. And that creates, of course, the classic QRS ECG. And we also had an invasive radial catheter in our patient population. We excluded that to the left side just to try to control a little bit more. because some of them have it in the right, depending on how easy it was to get the catheter inserted into the radial artery. But what we're really trying to look at is the time difference between that beat of the heart and how long did it take for that pulse wave to travel to the catheter. So the idea is built on the Bramwell-Hill equation that relates essentially the changes in volume and pressure to the time it takes for that pulse wave to travel. So the pulse wave velocity is going to be proportional to 1 over the pulse arrival time. How long did it take? And because that distance is unchanged, it's proportional. There's some argument out there that this is actually closer to 1 over the pulse arrival time squared. It's an active area of research. And in fact, if you Google papers on this topic, you'll find titles that are exactly contradictory. Some people say you can do it, some people say you can't. So we're trying to scale this using some of our machine learning tools to look at larger cohorts to really facilitate high throughput, high volume assessment so we can get at statistically powered results, which is a bit of a problem in the current literature. So how does this look in practice? This is a snippet from some of our data. Admittedly, it's a very nice snippet. There's a lot of parts of this real world data that do not look so pristine. So a lot of this project is built around quality control, quality investigation of the signal, not trying to calculate this where we can't find reliable peaks of the R peak or troughs of the systolic foot, so that this black trace here is your ECG. The dotted green trace is the arterial blood pressure signal that comes out of the radial catheter. And we're trying to figure out that time difference between the pulse of the heart and then what we call the systolic foot, where those red dots are. That's where the pressure starts to build because the wave has arrived. So we have an automated feature extraction solution for this. This is what a single patient looks like, where we fit a best fit line to a plot of the 1 over the pulse arrival time, just like we saw that being proportional to the pulse wave velocity in the previous slide, versus the pulse pressure or various measures of pressure. So we looked at this across pulse pressure, systolic pressure, diastolic pressure, or mean arterial pressure. But we found the most compelling results to be with the pulse pressure. So this is for one patient, and they have a pretty clear best fit line. You see a lot of scatter in there as well, because it's definitely not a truly linear system. There's certainly some nonlinearities that make this not an easy task. But we got data for 1,730 patients out of a total of 2,100. We had, like I said, those signal quality measures, so we lost a few hundred to not having good enough quality signals for long enough to construct proper best fit lines. But when we look at the whole cohort of the 1,700 and change group, we see this sort of distribution of the Pearson correlations with the pulse arrival time and the pulse pressure. So you can see that for the most part, people have a positive correlation. There are some that dip down into the negatives, which I think is part of the contribution to the discrepancy in the literature that we see. But the general trend is a positive correlation between those. But if you look at, for example, a correlation with the diastolic pressure and 1 over the pulse arrival time, the correlation there is not nearly as compelling. So across the whole cohort, we just wanted to look at the range of slopes. And so we just pulled out the median value of each quartile of the slopes versus pulse pressure. And this is just a plot of that to show you sort of the spectrum of vascular stiffness profiles that we see in the real world cohort. So there are some that have large change in the inverse of the pulse arrival time as you see the changes in the pulse pressure. And then there are some that have a relatively flat curve. So this sort of represents our spectrum of the characteristic profiles that we're getting from patients. And like I said, we published a letter on this earlier this year, and we are currently working to look at outcomes. So how does this relate to things like acute kidney injury or other potential negative outcomes from surgery? So if we can say, hey, patients with higher vascular stiffness profiles have higher risk, maybe there's an opportunity for physicians to provide additional treatment to help those patients. So again, that was built on our MLOps infrastructure, as was this wildly different, or maybe seemingly wildly different project on magnetoencephalography. So magnetoencephalography is a modality where you basically put your head into a giant machine and it measures the magnetic field fluctuations from firing neurons inside your brain. So these are really, really tiny signals, and like orders of magnitude more sensitive than even the background field of the Earth. So we have to have all this magnetic shielding and a whole lot of noise mitigation techniques to get reliable results out. And because it's so sensitive, even the tiniest little bit of physiological noise, like the beating heart or blinking eyes, show up as large signals in magnetoencephalography trace. This is also particularly exciting because if you follow the UAB news at all, it sounds like there's a new MEG, and I'm excited to talk to those guys and see if there's some collaboration opportunity. But this is a project I did a few years ago when I was working in a prior role, and we worked on building automated artifact extraction pipeline. So we can take the raw MEG data, we run it through independent component analysis, and then the independent component analysis tries to identify the dominant sources of signals. So a typical MEG has hundreds of channels. We distill that down to 20 independent components, capturing the majority of the variance in the data. And then you can see the artifacts from the heartbeat and the blinking usually occupy one or more of these independent component channels. So hopefully, if you look at this plot on the left, it might seem pretty clear that 13, for example, is your heart signal, the nice big R peaks that show up in this data. And then, for example, 19 looks like there's some ocular artifact there, less periodic, but large blips. And you can see on the topographic map that it kind of goes over top of the eyes a little bit. So we built a tool that does an automated AI extraction and uses these 1D time series and the 2D topographic maps to say, hey, this is a blink signal, this is a heartbeat signal, so that at least historically, we can take those signals out and have a better signal to noise ratio on our MEG signal. And you can see here the performance of this tool is great. But there's a lot of MEG data out there that is kind of standalone. And we had a problem where we wanted to actually look at autonomic function alongside the brain signals. And so in collaboration with some other folks at my prior job, we built out this methodology to extract the heart rate variability from magnetoencephalography signal. And the big selling point here, the thing that I think is most pronounced, tying it back to the MLOps, is this project almost never saw the light of day because it was happening as I was transitioning jobs. People were there was some issues with data reproducibility. There was issues with data quality and reliability. And so when I came to UAB, I was motivated to build this MLOps template. Kept getting messages from them. They wanted to see it through because this is supporting a lot of traumatic brain injury research. And so we worked together to put it into the template. And once it was in the template and we had our record keeping of what data went in, what data came out, how we got all of our answers, we started to see really consistent results. And they look a little something like this. So on the top row is the ECG signal. So we did this with 5 patients. It was admittedly a small cohort, and they were all demographically comparable, so not a great study by any means, but it was a proof of concept. We just wanted to see if we could do it. And you can see on the top for subject one was the, on the first columns is subject one, and they were the best performing subject in terms of root mean square error output. And in the column on the right is subject five. This was the worst performing subject in terms of root mean square error. But you can hopefully kind of line up the yellow dots from top to bottom and see that we are capturing, in fact, a pretty reliable peak identification from both sources of data. And we looked at the time domain, like I just showed. We looked at the frequency domain, very similar layout of the plots. You can see left to right, almost identical looking plots. And then we looked at the nonlinear domain for, and these are again, are just the best and worst performing. So I wanted to highlight who did really well and then who did really poorly, because, you know, these things are, this is real world data. Sometimes it's messy. And even in the case of Meg, just shifting about in your chair can cause a big source of error that might impact the ability for this to be reliable. But you can see again that overall, very comparable plots, and with some statistical tweaking, which I don't like to do as a physicist. I try to minimize my throwing away of data points as much as possible. You can see that if you were on the bottom right plot anyway, to remove those outliers and zoom in on the upper corner of that Poincaré plot, that it would match pretty closely to the one next to it. So because I was able to put this into our machine learning template, and we were able to really distill sections of our code down to small chunks, what I showed you in the first project about vascular stiffness, and what I showed you in the second project about magnetoencephalography, it had a similar portion of this pipeline that involved this ECG preprocessing and extraction of the RR intervals. So I had a really reliable instance of that from the magnetoencephalography project that was really easy for me to plop into the vascular stiffness project. I knew the packages, I knew the algorithms, and I had some code to call and do some bandpass filtering for the case of a heart, and it was ready to go. Really easy to just plop this into a different project because we used the template, we wrote our code in a modular fashion, and then made it really easy to just reuse it and plop it in, and it sped up the vascular stiffness effort. Okay, so those were both time series projects. I'm going to switch gears now to a more tabular project. Excuse me, this also recently was published in the Journal of Medical Systems. And here we wanted to help clinicians decide which patients were at risk for an escalation of care. And so as you have a surgery, there's a step down where you go from the intensive care maybe to a less intensely observed unit where, you know, there's not the 24/7 oversight as intensely. But sometimes patients go into those less intense units and then get put back into the more intense one because something bad happens. So we want to try to stop that from happening. Can we identify patients who are at largest risk for that escalation of care and maybe get out in front of it? So collaboration with Dr. Melvin and colleagues in the anesthesia department, we had a large cohort here. So this is a large data. We had initial cohort of almost 140,000 patients. Exclusion criteria took that down to about 60,000, but we were still in pretty good shape in terms of having a large statistical power backing this, with 44,000 in our training set, about 45,000 almost, and then 11,000 in the testing data. So really good population sizes here. And we built a risk model inspired by a credit score. And so a credit score is essentially a logistic regression model with weight of evidence binning. And one of the really nice things about this is it incorporates missing values, and in clinical EHR data, that is often the case. And so we wanted something that was both explainable for the clinicians and could accommodate missing values. And there's the results of our test set, holdout test set, had an AUC of about 0.76. And the thing that I find really interesting from this effort, I'll highlight these two elements from the plot here, is that these were missing values that got scored as a large risk factor. So measurement of the last hour SpO2 in the PACU, the post-anesthesia critical unit, and then the blood pressure in the last hour, the maximum blood pressure before leaving the PACU. And the missing values were highly predictive of being at risk for escalations of care. And the nice thing about this is that's hopefully, anyway, a pretty easy opportunity for intervention, right? If missing this is the problem, all you need to do is check to make sure that those values are there before you discharge them. And it seems pretty logical that if the values were not captured and people were making decisions that they should be released without seeing those values, maybe they weren't as fully informed as they could be. But there were other really critical things, the biggest one being non-surgical anesthesia time. So how long were they unconscious while not being operated on was the largest factor. But other things that came out also really jived with the clinical experience in terms of some of these value cutoffs where clinical intervention occurs. And so the clinicians were so happy to see the ranges of values, where things changed, and how it corroborated what they do clinically in terms of interventions for various situations. So like I said, the explainability was a really important piece to this. And this is something called Shapley values. Using Shapley values, we were able to estimate these trajectories for each individual patient. So this is ranked by the contribution to their probability. And then each of those lines is a patient's trajectory. So they maybe had a PACU blood pressure that didn't change things much, but then they had an AKI condition preoperatively that really moved them over to be high risk. And you can see if you look at the person here with the highest probability of 0.8 for an unplanned escalation of care, they had large swings once you got to AKI and non-surgical anesthesia time. That moved them over in a large way. So we're really trying to get to explainable models that clinicians can incorporate and ideally interpret and fold that interpretation into their clinical training, because some of these black box models aren't super helpful, particularly when they don't jive with what the clinicians expect. So we want as much as possible to help them know what the model's doing. So that's waveforms and then tabular data. And believe it or not, you've probably seen Dr. Melvin give a talk on this. The same idea of this MLOps template is at the heart of all of our generative AI tools. If you haven't heard us talk about it or seen it, you can snap that QR code and go play with our generative AI tools. But this looks like Ryan put the link in the chat as well if you'd like to click it. But it just speaks to the versatility of the tool. And I think if you notice, a lot of these publication years are this year. So this is a lot of work that's been done in a very short amount of time. And I attribute that anyway to the MLOps approach and having that consistency, the framework. And then as we bring people in, we can explain it. They know where things are, they know what to look for. And it all starts with automating with this cookie cutter template so that every time we start a new project, we get these very similarly shaped projects and we know where things are, we know what it looks like. And just one more plug for that with a QR code if you'd like to check it out. I'll leave this there for just a second as people are grabbing for their phones. All right, so some takeaways. There's a concept of dry, don't repeat yourself, bringing it back to the bridge building idea. It seemed really relevant. Stay dry, don't repeat yourself, right? The idea of a bridge is you want to stay dry. Build modular, reusable units. that will pay dividends in the long run for different projects. And it's great to be able to recognize in different projects where something you've done might be able to be reused. So for example, on our generative AI tools, we have a whole lot of consistent common code that we reuse in the different projects, because at the end of the day, we're just calling a large language model on the back end. And so we built to that interface. We have a suite of common code that is the same for every single generative AI project. And it's great. We've been able to abstract out the core functionalities of whether it's just a single response. Maybe you need to have chat history. Maybe you have some sort of retrieval mechanism, like a RAG, as well. So those are the three sort of frameworks that essentially all of our tools use. And we just have a common set of code. We build out a front end, and we just have to, all we have to do to build out a new generative AI tool at this point is to fill in the middle. And it's really expedited our ability to crank out projects and do so in a way that's really robust, really reliable, and hopefully useful. So upfront preparation saves time in the end and creates more robust products. So to link this back to the bridge building, right? You wouldn't start the Golden Gate Bridge without architectural diagrams, right? It just wouldn't happen. You probably wouldn't even start building the second bridge that I showed without getting your tools ready. You need to have your hammers and your nails and your planks and at least some idea in your mind what it's going to look like. So unless you just have that very bare bones proof of concept where you're just laying the plank across the bed of the river, having some upfront preparation is so important. And I spend a lot of my time in that space because it's really, I've seen the value of it over 15 years from my various jobs. So highly encourage upfront preparation. And even if I'm doing a very simple prototype proof of concept, I still use the MLOps template because we have a structure that allows us, hey, I proved the concept. Now I can fold it into the larger structure pretty easily. So I build out maybe a Jupyter notebook, prove it out, and then I can copy and paste those pieces into more reliable functions that are modular and easy to use. And then, yeah, make it easy to continuously evaluate your models, especially in healthcare, things like bias, model drift. There's all kinds of things that we have to evaluate in the terms of clinical applications. So we want to make it easy to do that. We want to simplify the process of saying, hey, this thing isn't working anymore without having to have some big push to test and record those values. Factoring in something like MLflow or deep eval, which we're definitely going to fold into our generative AI template soon. You want to be able to evaluate your model so that you know where you stand and know if you can trust the output or not. And then you will thank yourself and your collaborators if you make it easier to do right than wrong. Having the structure, having the style really supports these robust principles and how you can just really start to get high throughput with your work. And then by automating all this, it really allows you to focus on the fun part. So I wouldn't say any of the machine learning operation stuff is particularly fun, but it was one of the first things I did when I got to UAB because I saw the value in it. And I just wanted to be able to scale and expedite everything else I did from here on out by having that as a core tool. And it's really, I think, shown off by at least the publication throughput in the last year and the tools that hopefully you all have tried and enjoy to use on the generative AI side. Not to mention having some coding assistance from large language models doesn't hurt either. With that, I'll wrap it up. Here are a few hyperlinks. If the QR codes aren't your thing, you can type those in. There's a QR code for my contact. If you'd like to reach out, I'd be happy to hear from you. And I think we've got a little bit of time if there are any questions.
Well, thanks for the great presentation. Really kind of practical and born from your experience. I guess where, what are some places that you would say people can go to sort of get more hands-on experience?
Great question. And I should have mentioned it as I went through. I was a little worried about time. I know there's a lot of ground to cover and we started a little late, so I rushed through some of that, and I know there's a lot of ground to cover. So thanks for your attention on that. But one of the slides I had a little itty bitty thing in the top corner, made with ML. It's a fantastic resource. There are educational components for this concept of machine learning operations. Ganvis, I think is his name. Fantastic website. I think it's madewithml.com, and I highly recommend it if you're interested. A lot of what we showed today is adapted from the principles and the teachings that are captured in that website. So highly recommend checking that out if you'd like to learn more. I think I can put that in the chat as well. Confirm that's right though. Mahanis is his name.
Other comments or questions? Feel free to put them in the chat, or you can just unmute yourself too. We have lots of we have a bit of time. Oh, we have a chat here. Oh, that was your chat.
Yeah, the web link if anyone's interested. All right. Well, if there are any other questions, feel free to email me. I'm happy to hang out until the top of the hour. But I really appreciate y'all's attention and time, and won't keep you if you have other things to do.
Yeah, I think yeah, just a quiet crowd today.
No worries.
Kind of like Friday.
Kind of a scatter shot of different projects. It's probably maybe a little too much, but I just kind of wanted to demonstrate the power of the core by covering so much. So maybe isn't the best approach, but I think hopefully it demonstrated the power of our template.
Well, if you could share your slides, that'd be great. You know that not everybody, sometimes just want to look something up, not necessarily watch a whole recording. Right. Right. That's right. Ryan Melvin did show that other site. It is really powerful. All right. Well, thanks everybody for attending. Thanks, Dr. Godwin, for a great presentation, and see you at the next Power Talk. Have a great weekend. Right. Bye.
Bye.